Right. Okay, so we are continuing our discussion here on the discrete time Fourier transform, which is where we ended last week, Wednesday. We did a bit of manipulation to show how we went from the continuous domain to the, well, what we are calling at this point in time, the discrete time Fourier transform. And just share here. Okay, remember, if you have any questions, you're going to have to catch my attention. You have to say something. Okay, so let's start this. Right, so if you recalled, we said that one of the issues, of course, with the continuous time transform, which is, where are we? Right, that the continuous time transform operates on a continuous signal, which is not easy to manipulate. I mean, doing a continuous time integration is not something that you can do with a computer. And then when you get the answer is a continuous function of frequency, or either in radians or hertz. So plotting it is now a different a different issue. So what we said, okay, we said, okay, we have the continuous time domain. Let's convert that to a discrete signal by sampling. And we spent a lecture discussing sampling and some of the issues with sampling, including, most importantly, the how fast you have to sample. And we saw something called the Nyquist frequency, so that if you sampled by at least the Nyquist frequency, which was twice the highest frequency component of your signal, that you would be guaranteed that you did not have aliasing. And we saw that the reason that came about was because of something called spectrum replication in the sampled signal. So when you sampled a signal and you did a spectrum of the signal, what you got was the original spectrum of the signal appearing, but you also got this spectrum being replicated at instances of your sampling frequency. All right. And then we had a discussion on the sampling process and real sampling and ideal sampling and what was the differences between the two. The next step we said was, okay, well, if we have a sample signal and the sample signal we calling xt, and xt is your continuous time signal multiplied by the sampling train. Remember, the sampling train is really this bit here, the summation, and then you multiply that by xt, and it sifts out the values. So when you get that now, you have your sample signal, and then we put the sample signal into the Fourier series, or sorry, the continuous time Fourier transform, and we worked it out. And we did some manipulation, and again, we saw that because we're dealing with linear time invariant systems, the integral of a sum, you could swap these two. The integral of a sum of a sum of values is the sum of the individual integrals. And we did that, and then after some manipulation and shifting, we got down to a point where we were now able to define a new transform that we call a discrete time Fourier transform. So you have your signal, right? The signal is now a function of a frequency variable that we define by capital omega, and it's related to your continuous time variable by omega, the continuous time frequency domain signal that we know, which is 2 pi f, right? And ts, which is your sampling time. Or if you want to remember that omega is 2 pi f and ts is 1 over fs. So some people, and in some cases, it's convenient to record omega as simply 2 pi f over fs. And we'll meet that later on as we go through this thing. It will keep cropping up and so on. So omega is a digital frequency in radians, right? Because the hertz on top, it's really a dimensionless quantity, and it's related to just 2 pi, because the hertz part of the F on top and the Fs below, just simply those units cancel out. So we stopped there and we said, okay, that one of the issues here is that if you look at this particular function, omega is 2 pi F over Fs. If I increase omega to omega plus 2 pi radians, then we show that the spectrum of the omega plus 2 pi radians is the same as the original spectrum. In other words, the DTFT spectrum is periodic, and the period is just 2 pi radians. Okay, and again, if you look at that, if omega is 2 pi F over Fs, and I tell you now that this is now 2 pi. So you have 2 pi is equal to 2 pi F over Fs. What you're going to get is that F is equal to Fs. In other words, this is going to repeat itself every Fs, which is what we saw when we did sampling, that when you sample the signal, that the spectrum repeated itself every at the instances of every sample. Yeah? Everybody following that? At least acknowledge me, because I can't see the chat and I'll have to hear. That's all right?
Yes, sir.
Nice.
Yes, sir.
Good. So, and we did it over again just to make sure everybody understood what was happening. Right. So the implication of this is that the spectrum produced by the DTFT is 2 pi radians, or as we just saw, the same thing that we've been seeing. So you have your baseband. This is my original spectrum, whatever x of omega would be. And here it is repeated at 2 pi radians, or Fs, 2Fs, etc., which is exactly what we had before, which is nice. So how does this compare in the context of sampling? It's the same thing, right? And here's just what I just did, right? So that the mapping, everything that we saw about the Nyquist rate and so on, if Fs was to decrease, then this would move somewhere close here. And then at some point in time, you get this, right? So the signal, if you decrease Fs, at some point in time, you're going to get where this spectrum and the baseband spectrum will start to touch, and that is at the Nyquist frequency. So if the center frequency is 2 pi here, then this point is at pi radians, or twice the highest frequency of the signal. And the same thing that we've been saying all the time. Okay, and this is just a little proof right here, exactly what we just did. Right. So if I were to give you something like this is where we do some a little bit of calculation. If I give you something like this and I ask you, what is the continuous time Fourier transform for this signal? This is a pulse. The pulse, you have to apply it to this is my equation for the continuous time transform. Of course, minus infinity is going to run from minus 0.4 to 0.4. Let's assume the time is in seconds. 1 e to the minus j omega t. If you do that, you're going to get either this, or you could implement it in this form, which is how MATLAB implements it, the sinc function, right? But you could do the same thing, or you could leave it in E. If I were to integrate this, right, what I have here is the integral between minus 0.4 plus 0.4 xt is 1 e to the minus j omega t. So I could perform that integral. And I could perform that integral and I could get the answers either a function of E, or using Euler's equation, I could convert it to a function of sine or cosine. right? Which is where I have it in this point here. And then I could plot this, right? Now notice that they x omega, which is a continuous time Fourier transform, gives me a continuous function of S. All right, let me ask you a question. Let me just stop sharing for a second. If I were to ask you all, like from your AdMaths days, to plot x equal to t squared, what do you do? Right? I ask you to plot x equal to t squared. What do you do? Is that a continuous or a discrete function?
Continuous one.
Right, it's a continuous function. So I ask you to plot on a piece of paper s x equal to t squared. Or to sketch it. What do you do?
You plot the points.
Right, what points?
Maybe points at different samples of x equal
right.
to t squared.
Right. So notice what you're doing. Xt is a continuous time, x equal t squared is a continuous time function. But to plot it or to sketch it, you pick values. You actually sample it. So you sample it and you let t equal to 0, you let t equal to 1, you let t equal to 2, that kind of thing. You put those points and then you connect all the points with a continuous line. And the assumption, of course, is that because it's continuous, that continuous line will represent the uniform variation from 0 to 1 and 1 to 2 and 0 to -1, etc. And you get the actual smooth curve. But you realize what you actually do, that even if you have to plot a continuous time signal, you have to pick values, discrete values, and plot it, and then assume that they have a nice continuous connection between the two consecutive points, right? So, yeah, and it's similar. If I were to ask you to plot x equal to t cubed, you could pick some samples, but if you pick the wrong samples, you could actually have the thing not being, not looking like how it's supposed to look, which is there's an inflection and you could get some strange, if you plot it with too large spacing, then you end up getting the wrong thing. So it's the same thing here. When we go back, right. You all seeing this?
Yes, sir.
Yes, sir.
The full screen or just to make sure, because I'm not too sure. Are you seeing the one with the sync function on it?
The
Yes.
full screen, yeah.
Good, nice. Right, so it's a continuous function of S, but if you want to plot it, you really have to pick some values of F to plot. So although it's continuous, you have to sort of discretize this in your mind or apply some values of F, 0.1, 0.2, 0.3, or whatever it is, and then connect the points. Which is why I'm making the point that at this point, if I were to just tell MATLAB, plot this, just put that function, plot x equal 0.8 sync 0.8f, and I don't give it any values of f to go by, it's just going to sit down and watch me, which is why the manipulation of this is not possible by a computer until you tell it specifically what points to plot, and then it will do a connect the points. All right. So in a funny way, when we try to display continuous information, to display the continuous information, we have to pick discrete points, if you get what I'm saying. All right. So if you plot the magnitude of that, the square, a rectangular pulse, we get a function looking like this, which we know we've done this countless times already in time gone by. This is the magnitude of the function. Remember, the real function does this, and it goes on and on and on and on. All right. So this is the magnitude spectrum of the single pulse, a single pulse that is about 0.8 seconds in width, and one, so let's say it's a 1 volt signal, and it's 0.8 seconds wide. You do the spectrum of it, you get something looking like this. At 0 frequency, you have 0.8 volts, and then somewhere at 2 hertz, you have another spike, which actually is negative. It will be a negative signal. This is just a magnitude. At 3 hertz, you're going to have something. At 5 hertz, thereabouts, and so on. So you can get an idea that this particular signal has a number of frequency components in it. And because we're dealing with the continuous time spectrum, this spectrum goes on and on and on. Yeah. The zero frequency, of course, is a DC value, right? And you should be able to, if you remember when we did this signal, something that starts at 0, goes up to 1, and then back down for 0, over a period of time, this behaves as at least as though it has some sort of DC value plus the frequency components in it. All right? Right. So let's do a little bit more now, and let's sample the signal and then apply the discrete time transform to it. So I take this the same signal that I have running from minus 0.4 to 0.4 seconds, and I sample it every 2 seconds. So if I do this, I get 5 samples that I have here. So I know, and the samples, of course, will be my xn will be simply, what do you call it? 1, 1, 1, 1, 1. Those are my 5 samples. And the samples running from minus 0.4 seconds to 0.4 seconds. So this is, if I've sampled correctly, I don't know what it is, but I'm doing 5 samples here. Let's see what happens. So I now take that, and I now plug that into my equation for the discrete time Fourier transform, the DTFT. If I do that, of course, I'm going to sum from the sample values now are going to sum. Remember this is n here. This is n. This is sample minus 2, minus 1, 0, 1, and 2. So the samples, instead of running from minus infinity to infinity, run from minus 2 to 2. Those are my 5 samples. And of course, all the samples are 1, which is why I do have it inside of here. And if you do that and you expand it, this is what you get. Right? I'm using f here. Remember, f is 1 over ts. Okay? So I am now in a position I can plot this.
So I have a question.
Yeah.
Why was it running from minus 2 to 2?
Okay, let me go back here a little bit. Right. This is remember, this is the equation for the DTFT. It sums from the sample number, n equal minus infinity to infinity. Right? So each of the samples of n, right, and n run from minus infinity to infinity. I have samples, 5 samples, and my samples, instead of running from minus infinity, run from, this is sample 0, this is sample minus 1, this is sample minus 2. This is sample 1, and this is sample 2, right? So in other words, n is running from minus 2 to plus 2. Yeah?
All right, thanks.
And the omega part comes in here because omega is 2 pi omega is 2 pi f over fs, right? Fs is 1 over t, which is 0.2. So if I put that in here, omega is 0.4 pi f. Yeah? So if I substitute here for the omegas, then expand that, this is what I get. Just straight expansion. Everybody following? Right? In other words, this is simply, this is, if I sum from minus 2, this is minus 2 e to the minus j minus 2 omega, right? Plus -1, which will be minus e to the minus j -1 omega plus 0, e to the 0 will be +1 plus, and then we repeat this. It will be e to the j +1 and then e to the j +2. So you get this. And then you substitute for omega. We all right? Make sense?
Yes, sir.
Yeah.
Good. And now what I do is that I plot x omega. So I could put this in this form. I can leave it so, or I could put it as you could realize, this actually turns out to be a real thing. The e.8 and e to the minus j.8 is actually cosine. So it's a real function here, it's turning out. So I could plot this. X omega is equal to 1 plus 2 cosine 0.4 pi f plus 2 cosine, etc., etc. Right? If I do that and I plot it, this is what I get for the magnitude of that spectrum. So comments, what are you observing here?
The spectrum of the original pulse repeats itself now.
Right? We have a replication going on. This is what the spectrum is supposed to look like. We take 5 samples, run the DTFT on it, and plot the spectrum. And you notice that the spectrum is repeating itself. Now, what is my sampling frequency?
0.5.
5, right? This sampling frequency, right? TS was 0.2. So Fs is 1 over that, which is 5 hertz, right? Remember, we just said that the spectrum would replicate itself at the instances of Fs. Look at this. This is 5 hertz. This is 10 hertz. This is -5, -10. So the spectrum is replicating itself every 5 hertz. Right? We did that. We show that. We now seeing that is really happening when you plot it out. Let's put the continuous time transform and the discrete time transform next to each other. So what we have on the left-hand side is what the quote-unquote real spectrum is supposed to look like, the magnitude. And what we have on the right is what we have at DTFT, which is just 5 samples, and we did the manipulation. What do you find about the comparison? How does this look? It seems to be a decent representation, doesn't it? Yeah, no, maybe.
Yes, sir.
Right? The one on the left is what is supposed to be. The one on the right is just a sample. We have taken 5 samples, just 5, run the DTFT on it, manually plot it, because it's a continuous function of frequency, so I still have to pick some values on plot. And if we look at both of them, comparing them, what is being detected on the left is sort of being picked up on the right. I mean, we have some things that we have to talk about. First, the amplitude here, right? But we'll spoke about that. But then look at this. The DTFT is giving me 0 at 1, 0 at 2, 0 at 3. But in fact, the real spectrum is not 0 at 1, is not 0 at 2, and it's not 0 at 3. So we have some little, clearly we have some differences, but we just 5 samples, and we have something that from a representation point of view is fairly close. So let's see if we could improve on that. I sample at 1 second. So in other words, I sample at 10 hertz instead. So I have samples going from -4 to 4. So I've gone from 5 to 9 samples now. If I run the spectrum again, do the same calculation that I had before, right? On paper, because it's continuous time, so I can ask a computer to do this. If I do it on paper, and then I get the answer, I can plot out that. Notice that I'm now sampling at 10 Hertz, and the spectrum is repeating itself at 10 and at minus 10. So let's zoom again, right? So this is the good one on the left, quote unquote, and the 9 sample one on the right. Notice that we're starting to get a little bit better now. It's not 0 at 1, it's not 0 at 2, it's not 0 at 3. So the 9 samples are giving us a more closer representation of what the real spectrum of that pulse is supposed to be. Through an approximation. And let's put them side by side. Right, so the 5 sample one is on the left, and the 9 sample one is on the right. Okay, so first off, comments on this. So what do you observe?
Well, the one with more samples tend to have more information to go off of, so it could more accurately represent the frequency domain of the signal.
Right, so you're getting into a position now where the more samples is giving us a better representation of the original signal. Now, bear in mind, we spoke about something called the Nyquist frequency. If I have a pulse, this sharp transition from 1 to 0, right? Remember the spectrum of this goes on and on and on and on, technically to infinity. So no matter how fast, how many samples of this pulse I take, I will never be able to sample at exactly the Nyquist frequency for that pulse, just because of the fact that the real spectrum goes on and on and on up to very high frequency. So I can never really sample at the Nyquist frequency. So I will always, no matter how many samples I take, I will always have some inaccuracies occurring, and I have to be aware of that. There's part of the world of signal processing that at some point in time, you always will be still dealing with an approximation. But clearly, just by going from simply 5 to 9 samples, I've already started to get to this situation where, let me put back the real right. So the true on the approximation, just a 9 sample one is significantly closer to the true signal than was the original one. The one other thing you have to look at too is the amplitude, right? Notice that the 5 sample one has an amplitude of 5. The 9 sample one has an amplitude of 9. Okay, for this particular function. We will see later on that when you're implementing things like the Fourier transform, the fast Fourier transform and so on, to get the correct magnitude, you have to divide by the number of samples. And we will see why that happens. It has to do with the energy of the signal. So if I were to divide this by 5 and divide this by 9, then the actual amplitude of the spectrum will come back down to where it was supposed to be. Yeah? Everybody okay with that? Right? So both of them resolve essentially the same frequency components because the shape is consistent. The difference in amplitudes, we just mentioned that. And as was said there, we can improve the performance of this by using more samples in the analysis. The thing about it is that this, remember, the x omega is equal to an infinite sum e to the minus j n omega. This is an infinite sum. So the bigger, when I had the original 5 samples went from -2 to +2. If I took 9 samples, it went from -4 to +4. Okay, So if I were to take, keep increasing this thing, it's going to go from some minus number to some other one. And all of this, I have to do manually. Right? I can't ask a computer to evaluate it because all of the components here, just 2 pi f over fs business here. F is a continuous component, is a continuous variable. So I have to do this manually up to the point where I can ask it to plot. And then I still have to pick some values to have it to plot and make some assumptions, all right? So we're not yet at the point where I could just simply give my system xn. Somehow I came up with xn. Say, okay, here, look xn, give me the spectrum for that. I'm not yet at that point, right? I could do some mechanical work and still tell it. And then, and after I do the handwork, then I'm in a position to tell it to do the plotting for me. Right, we just mentioned this, so the pulse has a high frequency component, so we will always have aliasing, and that will always cause some of the differences in the amplitude spectra that we have, right? So as with the continuous time Fourier transform, right? So maybe right up here, right, where you see this, you can just put a little note. This is the continuous time Fourier transform. As with the continuous time Fourier transform, there is an inverse DTFT. Remember I told you, if you go from time to frequency, you must have a way of coming back from frequency to time. Otherwise, the transform is no use for you. This is how you get the transform, the inverse DTFT. Notice that this is because omega is still a continuous function of frequency. You have to do an integral. So there's no way I could do a forward transform to go into the frequency domain and then have any computer do this. And in fact, this is a complex integral, right? So even if you're doing it by hand, this is not a particularly easy integral to do. It's complex in integration of complex numbers, and you have to do that in a particular way. All right. So still useless, right? Right, still useless for DSP work. However, we're making some progress. We are seeing that first off, that the frequency range, it goes from 0 to 2 pi, and we know how to convert the 2 pi back to radians. And it gives us, to be most accurate, it gives us a continuous frequency spectrum, and it requires an infinite sequence really to work. All right, so we're making progress, but we still not quite useful as we would like. And just to look at some comparisons here. The continuous time Fourier transform, this is the discrete time transform here. The inverse, all right? So kind of similar up to a point. If you look at the behavior, actually, if you compare the Fourier series with the DTFT, because remember the Fourier series has a summation, it's a sum of these individual, what do you call it, indices here, coefficients. If you compare the Fourier series and the DTFT, you notice that the behavior mathematically is very, very similar. And in fact, if I were to compare these two, look at these two here. If I replace CK with XN, all right, then replace T, show it here, replace CK with XN, replace T, common T with minus omega. So this T, I replace with minus omega, and then remember this, that T naught, the fundamental is 2 pi. Then if I make those substitutions here with the Fourier series, then I actually obtain the the discrete time Fourier transform. All right, so there's a close relation with the Fourier series equations and the DTFT. This is just for knowledge sake, right? I'm not going to test you on this and ask you to prove it, but it's a very interesting thing that the Fourier series, which works with some discrete values, remember it works with discrete values of omega naught and discrete coefficients values C1, C2, C0, etc. And the DTFT, which is working on discrete values of the signal, x0, x1, x2, x3, etc., that the both of them are so closely related. Yeah. So questions? Everybody all right with that? Yeah, no, maybe. Let me hear you. Everybody following?
Yes, sir.
Okay, right. So this is it for today. What I'm going to do tomorrow morning, sorry, not tomorrow, Wednesday morning, we're going to see, first off, we still got to work with this thing. It is, although we're taking samples, the summation is infinite. And then if we go to frequency, I still got to come back from the frequency domain because the integral is a continuous complex integral, complex number integral. So I can't do that. So next time what we're going to see is if we can make some more approximations to this thing that will allow us now to simply take the continuous time signal, sample it properly, and with a fixed number of samples, put it inside of there and just write a bit of software to say, okay, these are my X samples here. Give me the spectrum of that. And it will follow a set of steps without me having to manually do any integration and manually do any manipulation and so on. And let's see what we land up with. Okay, so we're leading into something that is more robust and getting into something that we will see on Wednesday morning. All right. Just as an aside, the Wednesday morning class will be 1 hour long. All right, because we have a quality assurance visit here and the meeting is starting at 9. So I'll run the class from 8 to 9, and then well you have an hour off. All right. And problem set 1 is now available for you to try. All right, it's simple. It's a simple revision just to let you to reinforce some of the ideas that we were doing. There were some things that I asked you to try in MATLAB. You're not going to be tested on MATLAB, but it's good to illustrate some of the discrete time functions. And when you have the samples, to shift them around in time. Remember, MATLAB indexes from 1, whereas some of our calculations actually index from 0. So just remember that, and you could see what sort of answers you get if you try them out. All right. Okay, let me stop the recording here. Was anybody able to